different amount was the tool or the component they can use to make a chip during the process. And we are going to talk about that in a few minutes. In the future? Okay, just summary for this unit. Most transistors are stacked on gate, oxide, and silicon to form the transistor, and then can connect them to come in the circuit. Act an electrically controlled circuit, either on or off, controlled by the terminal, the gate terminal. Build logic gate out of switching. Okay, and we draw mask to specify layout of transistor. Okay, let's move on. Let's go to look at unit 1. We're looking into the detail of the circuit and the manufacturing process. Not in depth, but just give you some idea how the manufacturing process would look like. Circuit and layout. In this unit, we are going to describe the fabrication process. And in unit 0, just give you some basic understanding. But in here, we are going to talk into the detail of the circuit design based on the transistor to build the logic gate. And also another kind of circuit family, patch transistor. And then we talk about how to design latch and flip-flop of the memory component. And what is standard cell layout, the diagram to simplify layout schematics. Okay, this picture shows the inside of the foundry factory. Chips are built in huge factory called fab, inside fab. And the fab contains clean room. And the clean room can be as large as a football field. So that's quite large. If you go to the Hsinchu industrial park, you can see either TSMC or UMC companies, they have huge building. The inside the building, that factory contains clean room. You can see that they have to wear the special clothes such that they will not get dust particle into the clean room. Otherwise, the particle can destroy the chip during the manufacturing process. Even a single particle can destroy a chip. So we are going to talk about fabrication step. We start from the silicon wafer, the blank wafer, nothing there. Actually, there's some kind of the cylinder, and they can slice it into wafer. And slice it into very thin. Build an inverter from the bottom up. Just take like inverter example. First step would be to form the end wafer, your silicon P substrate. How you are going to build the end wafer? In first step, first of all, we cover wafer with protective layer SiO2 is an oxide， 二氧化系，这是一个细的氧化物。SiO2 is going to be an insulator. And then when we remove layer, where anywhere should be built, somewhere around it. And implant or diffuse any dopant into its pore wafer to get the anywhere. And then we strip off the SiO2 on the color. Let's look at the following slide. First of all, we cover wafer with protective layer of SiO2. How do we do that? We grow SiO2 on top of Si wafer by putting the wafer in the oxidation furnace. 这里是用锅炉，可以烤，可以烘的那种锅炉，非常高的温度 ，very very high degree， 900 to 1,200 Celsius degree, very very hot. With H2O or O2, such that we are going to build a layer on top. SiO2, okay, in the furnace, heated very high temperature. So that's the SiO2. The silicon and then oxidation, we get SiO2, the layer on top of that. Next step, we spin off photoresist. Photoresist is a kind of material. Is sensitive to light. Photoresist is a light-sensitive organic polymer. 这是光阻剂它们会涂在上面。它本身是一个对光敏感会受到它的化学变化的一种有机物质。And the photoresist is going to be softened where it's exposed to light. And that's why, that's how the mask comes into play in the process. If we are going to put mask on top, from there some distance, the mask here, the light going from the top through the mask and on the wafer. So this is the mask. Remember the anywhere. We have a layer anywhere in the last slide. Okay, here, right? In anywhere, the gray rectangular is anywhere. We are going to put on top, below the wafer, the light from the very top. Emit the light through mask, the geometric shape. This is the mask for the well. It's taught photoresist through anywhere mask. The dashed line is the cross section. You cut through the wafer, okay? And this is from top toward the bottom is the mask. Between light emitting source and the wafer is the mask. And only this rectangular will let the light go through. Shade on the top of the wafer, such that the photoresist is going to be softened. And you can remove that is called photoresist. Any questions so far? 问题？你今天用光照挡在光源跟细菌之间，那光通过光照的形状。这几个区域，这块长方形区是可以通过光的部分，会照在 silicon 的上面，这个光子基本身被软化掉，那之后就可以把它去除掉了。那其他会继续留在上面。Next step we are going to roll the wire material. We etch oxide with hydrofluoric acid, HF, the very nasty stuff, very poisonous. 这是一个非常毒性很强的一种材料，它甚至可以穿透你的皮肤，吃到你的骨头都有可能。所以军场里面的那些化学药，其实实际上是很危险的，不要碰触到。It only attacks oxide where this liquid is cold. Let's say we have this so far, and by using the HF, you remove this part. This SiO2 will be removed. If there's a joining shape here, it only attacks oxide where the resist has been exposed. For this part, there's no exposed at all. So SiO2 is still there. For this SiO2, it's gone. And then you can strip photoresist. Take off the photoresist. Now we have already built the layer of SiO2 on silicon wafer. Using neutral acid or piranha H, 这是食人鱼它也是毒剂嘛，这是一种酸。Necessary, so this doesn't melt the next step. What's next? Then we can try to go the anywhere. The anywhere is formed with diffusion or ion implantation. There are two approaches. One is diffusion. Put the silicon in a furnace, and then we can diffuse the element into the silicon wafer to form the anywhere. We create a wafer, we furnish with arsenic gas. Arsenic element into the silicon, it becomes N-type material, anywhere. Heat until arsenic atom diffuse into the whole silicon. This is the whole surface. Then the arsenic atom will diffuse into the wafer. 所以你今天在锅里面烧，温度非常高，使它的这个砷不是砷 element will diffuse into the silicon. 这砷的原子将会被散布进去里面。The other approach is ion implantation. Ion is the ion implantation blast wafer with beam of arsenic ion from the top. Okay, we'll go through the empty layer here and go into the silicon implantation. The ion is going to be blocked by SiO2. This area is blocked. It only enters the total silicon. Okay? Either way. Nowadays, ion implantation is more popular. Before, probably diffusion is more popular. Any questions? And we can again strip oxide, remove the top layer of the oxide. The reason why we want to have this oxide SiO2 is we want to grow or build in any way inside the silicon wafer. And back to bare wafer with any wafer. Now we are done for the first layer, that's any wafer. The subsequent step involve similar steps. Just between the first major step. In the major first step, there are several small steps. 后面的各个 layer，one layer，another layer，another layer，just follow similar process step, and you can get the real chip, the real circuit. How about the second layer? Before we go to second, we are going to have thin gate oxide again, like before. You can roll the gate oxide on the top. And then the deposit thin layer of gate oxide must be very, very thin. Otherwise, you cannot get a good capacitor for a traditional. Less than 20 angstrom. 假如20I, what's the unit for the angstrom? The 10 to the 10 order meters, okay? Very, very thin. It's about 6 or 7 atomic layers. And then again, hitting the furnace, the chemical vapor deposition of CVD of silicon layer. When wafer in furnace with ceramic gas, and form many small crystals called polysilicon here. And heavy load to be good conductor. If the element density is good enough, high enough, you are going to get heavy load there, and that's going to be a good conductor. Maybe what it's not as good as metal, but still good conductor even. This is not too long. And again, we use the mask, the polysilicon mask here. This form, you should be able to remember the layout. We have a polysilicon layer, right? And that's a mask in the geometric shape, and to again to lithography to pattern the polysilicon, either the iron implantation or diffuse the element. But either way, eventually you are getting the polysilicon on top of the insulator, like this. This is a cross-section view, this is a top view. And then we use oxide and masking to distort where N diffusion, the N open should be diffused or implanted, either diffused or implanted. And N diffusion form N1 salt join at anywhere contact. That's what we are going to do. It's not done yet. The divide, the silicon wafer we now have, but we are going to do this. Using again mask. This is A diffusion layer mask. Pattern oxide and form a region like this. Okay, again, through the mask line going through the mask, and this area is going to be exposed. But for this part, it's being blocked by the polysilicon. So there's no hole, only these are holes. Okay? Likewise, this is the hole. And we are going to implant, diffuse, and material in here. Okay? And diffusion here. This is for wear tag. This is for source terminal. This is for drain terminal. Like this. Open, diffuse. Now then, is ion implantation. But regions are still called diffusion in terms of the term, the name. And after that, strip of oxide to complete patterning step. Again, we remove the oxide material. Oh, by the way, it's called self-aligned process. What does it mean? It means that this polysilicon is blocked right there. So only this region and this region are important. If you are not using any mask for this, okay, you given the mask like this. The polysilicon is here, so it's set line. Use the polysilicon as part of the masking. And why do we use the polysilicon instead of metal? Because polysilicon is better than metal for set-aligned gate. It doesn't melt during later processing. It also indicates that if metal is going to be melted for the later processing. So polysilicon is good for set-alignment, although it's not as good conductivity as the metal, but it should be enough. The distance is short, not long. So after you strip off the oxide, we complete the patterning step for the end diffusion. Now we have end well, polysilicon, end diffusion, ready. And then P diffusion, again, using P diffusion mask. Okay, mask. Sitting between the ion implantation emitting source. So only this mask, the ion can go through, the ion beam can go through. So implant into the silicon right here and get seven ion. So this part is no diffusion in this side. And then we have contact, like I said, contact are just like hole. Before this step, we grow again, we grow the insulator, and then only these are big hole right there. Okay. Using the pattern. We cover chip with thick field oxide. Thick field oxide and edge oxide where contact are needed. This cut the hole. Cut. Why do we need to cut? Because we want to connect the P substrate through this conductor. Connect to the ground or M1 transistor. Connect the N wave through the N diffusion and through the conductor, through the PDD plus PDD. And finally, the metal layer to cover on top using the pattern here. And this is the ground terminal, is output is for PDD, and the red is polysilicon, and the input for the inverter. Okay, now that's complete. Now that's the final step of the chip manufacturing. But in this case, there's only one layer of metal. But actually, in industry, they can grow quite a few layers of metal. So just like the highway, there can be a 3D highway network, not just one level, but several levels of the metal connection wiring between the different devices, including the contact to go down to connect the device. There's only one layer. We can build like 7 layers or even 9 layers of metal. 就像立体交通网一样，它的 metal 是有连接线，是导线，你可以有立体的方式去。At least you want to have 2 layers of metal because horizontal and vertical wire, they should not touch together to connect together, just passing through. So you have at least 2 layers of metal, right? one for vertical, one for horizontal, as it's true. And when you want to connect the device underneath, then you have contact going down, right? Okay.我觉得我们今天在layout上面可以有2层以上的 metal 来做立体连接，因为你至少需要导线能够走横的、走直的交错或没有连接，不然你这样，否则的话你要避开。If there's only one layer for metal, it's going to be very, very difficult to connect different devices in the layout, right? 你要避开一些 device， 不然它会碰到别的地方会连接，它必须要绕开，让导线不会碰在一起。那最好方法是刚才用立体的 vertical separation between the different layers of the metal, such that they can really suit each other, okay? Without contact. So, what is layout? Layout, the chip are specified with set of masks. As I said, during the process, you need the mask. The minimum dimension of the mask determine transistor size, right? The exact mask, the exact layout, indicate the real shape of the chip of the circuit. 它就代表真实的形状跟大小跟位置。And also the transistor size determine the dimension of the transistor, including the length, the width. That determines the speed, the current, and power. The smaller, the faster. The smaller chip area, right? The cost. And the smaller, is faster and it consumes less power. And we define the term feature size F. The feature size F is what? The feature size is defined as the distance between source terminal and drain terminal for the transistor. For the minimum transistor, let me repeat it. Feature size F is defined for the distance between the source and the drain of the minimum size transistor. Okay. And that equal to the minimum width of the polysilicon. So what does that mean? Try to remember this definition. The distance between source and drain, or minimum depth width of polysilicon. And then let's go back to the figure. Maybe here. So what is the feature size? Where is it? Where is the feature size? How long was the distance? Feature size. Let's say feature size is the distance between source and drain. What source and drain of the minimum size transistor. And that's going to be minimum width of the polysilicon. So this is the feature size. This is the feature size. Okay? Is that clear? If this is the minimum transistor you can manufacture in this process, the channel length is the channel length, right? Beneath it is the channel connecting source and drain, right? Is the channel length, and the channel length or the width of the polysilicon. We define that as feature size. And the feature size indicates how small can manufacture on the silicon chip. The smaller the feature size, the more advanced for the manufacturing process. You can make very small transistor. And the smaller transistor size, you can put more transistor on a single chip. VLSI 就是它的这个制程水准。So when we talk about like 7 nanometer or 5 nanometer or 3 nanometer, that's a VLSI. That is VLSI. Meaning we can make the minimum size transistor with channel length equal to 7 nanometer or 5 nanometer or 6 nanometer. And 3 nanometer is more advanced because the transistor is smaller. You can put more transistor count, higher transistor count on a single chip. 就越小的 VLSI 代表制程越高的水准 ，higher level for the manufacturing level. Technology more advanced. And nowadays we are around 3 nanometer, the current technology. Now, if you want to make larger than the minimum transistor size, no problem. If you can make such small transistor, of course you are able to manufacture larger transistor. However, the opposite is not true. You can make a small transistor with channel length 3 nanometer. Doesn't mean that you can make a good 2 nanometer channel length transistor. Because the equipment, the process is not so accurate. You are not going to get a working transistor using 2 nanometer. In 3 nanometer technology process. And from history, VLSI improved about 30% every 3 years or so. 每3年，我们的 VLSI 就缩小30%， so it's about 0.7 in 1 dimension. So in terms of chip area, it's going to be 0.7 times 0.7. It's about 1/2. Meaning what? Meaning given the same circuit from this generation to the next generation with 3 years between them. After 3 years, the next generation are going to give you the same circuit but only 1/2 in terms of chip size, in terms of chip area. 就每隔一代，就至少过去比较粗的分的那种一代一代 each generation about 3 years, and you are shrinking the transistor size such that it's about 1/2 in terms of chip area. 它是占1/2的面积，一个 1 dimension is 70%, y dimension is 70%, so totally the chip area 2D is about 0.5, about 1/2. So you can put double transistor count, right, on the same chip area. 所以相对来就代表 from this generation to next generation, you can put double transistor number onto the same chip area. A normal line for VLSI when describing design rule. So given the same circuit, the same layout, from this generation to next generation, if your relative geometric features are the same, you're simply using F, the VLSI, the basic display unit. You don't have to modify the circuit. 电路其实并没有改变，从这一代到下一代，因为这个就会说 you are thinking everything into 1/2 in terms of chip area. The transistor smaller, and their relative sizing, the relative distance are the same, proportional to the feature size. Okay? Actually, we have another term which is lambda. Lambda is 1/2 the feature size. So given the technology process, 0.6 micron is 600 nanometer process. The lambda is going to be 1/2, 0.3 micron. You might wonder why we need lambda. We have F because for the transistor like this, the first second is 2 lambda. Let's look at the layout. In many design process, let's go to the other one. In many design process, the layout is here. Let's say where the feature side is the width of the first signal, the minimum first signal width. Also, the channel length for the minimum transistor, smallest transistor. And it's F. However, in the other material, for example, for the metal here, you need 1.5 F. So it's not convenient. So that's why we come up with the 2 lambda. Feature side F equal to 2 lambda. And the first minimum per second 2 lambda, the metal equal to 3 lambda. The integer unit 3 lambda. So that's why we come up with another, it's called lambda, 1 half of the feature side. But the feature side indicates the minimum transistor side, the channel length. 什么呢？feature side 代表一个制程的水准，讲我们3纳米、5纳米、7纳米，在讲它的feature side，它代表是能够制造出来最小的transistor它的 channel length， 也代表这个transistor它的大小。那它的2lambda，用lambda做单位，因为有些需要2lambda，有些需要至少3lambda，像至少是整数的lambda。Go back to unit 1. Okay, we are here. It's about layout. Any question? 有问题？制程在进步，就是一直萎缩。The manufacturing process keep advancing means that you are shrinking the feature side, you are shrinking the transistor side, smaller and smaller and smaller. Such that getting faster and faster, consume less and less power per transistor. So unit lambda is the basic unit. This is for a specific process, the design rule, the motion in California. But for the other foundry, for the other manufacturer like TSMC or UMC, they are going to have their specific design rule. How wide for the polysilicon, how wide for the channel length, how wide for the metal. But they will be different from each other. Conductive rule to get you started. You have to design, have the layout, meeting the requirement of the design rule like this. Otherwise, the manufacturer does not guarantee that you are getting good chip. Probably most of the chip in manufacturing are going to fail because you do not have enough like metal wire, then each metal wire has to be 4 lambda. And between 2 metal wire, it has to again 4 lambda. And metal 1, the first layer. The second layer, metal 2, also 4 lambda for width, 4 lambda for spacing. Diffusion layer, again 4 lambda for the width and the spacing. The first silicon, 2 lambda. And I said, first silicon width. But between two polysilicon, it has to be 3 lambda. It is minimum 3 lambda. So forth. For example, this polysilicon above PMOS transistor, NMOS transistor. It is a PMOS transistor. And also, the well and N well contain PMOS transistor, it has to be 6 lambda. From boundary to the diffusion. From boundary to the diffusion transistor, 6 lambda. And the polysilicon has to be over, on top of the diffusion to form the transistor, you have to go over at least 2 lambda. Otherwise, it's a negative, the manufacturing, the negative T back is going to be working. Besides that, also the contact, we call that contact or wear tag, substrate tag. That wrap up is the cut, just like a hole, such that they can connect different layers. It has to be 2 lambda wide and 1 lambda between the boundary and the metal layer. Okay. Between metal 1 and diffusion, connecting the different layers, metal 1 to diffusion, the contact, different layers, metal 1 and polysilicon, the contact, the unique contact to connect different layers. Like this. This contact is connect metal layer and polysilicon. Okay? And they can also connect metal with the polysilicon. It's not shown in the video. And also there are some requirements. You have to meet the spacing and the width. Otherwise, it does not be like any working circuit. And between metal 1 and metal 2, they can also connect different layers, just different flow, connected by the elevator. And why is that? Why do we need that? Why do we have to meet the requirement? At least, it's not exact same number, but at least it has to be 6 lambda. 5 lambda, 6 lambda, fine. 5 lambda, 6 lambda for the spacing, fine. But it cannot be 3 lambda. Otherwise, it could be 40. Why is that? Because the accuracy is limited for the specific process. You cannot make even small, no way. It has to be at least some size. Otherwise, the accuracy of the equipment cannot manufacture good chip, good circuit. If you do not have 4 lambda between 2 metal wire, it could be possible that somehow they touch together. Okay, see? The wire, because the inaccuracy, they could be too close to each other, and somehow they touch together. 2 wires can touch together, which is wrong, right? And also the width. Why we need to require the width? Because the accuracy of the equipment, if too short or too narrow, it could be something like that. It's broken. Because the inaccuracy of the manufacturing process, it could be broken for the wire. That's why we have to define a rule, a set of rules. That's a minimum requirement. Otherwise, the language will be like this. Okay, let's take a break.